The non-invasive glucose measurement is a much sought-after technology, especially by diabetics who prick their fingers multiple times every day just to keep track of their glucose levels. Using only light to penetrate the body, non-invasive glucose measurement is painless, convenient, and has the potential to be very inexpensive. But this dream is not as easy as it may seem. About 20 years ago, infrared spectroscopy was proposed as a likely method for non-invasive glucose measurement, and initial results did look promising. The first peer-review article on the topic was authored by Reese Robinson, the CEO of Medici Technologies. Though the idea has been around for decades, its history is littered with failed attempts. But despite the historical failures, by applying technological advancements in other fields to this difficult problem, it's now possible to measure glucose non-invasively. To fully appreciate the solution, you need an understanding of infrared spectroscopy and the assumptions on which it's based. Quantitative infrared spectroscopy allows for a concentration measurement to be made of a specific molecule using infrared light. The wavelengths of infrared light are slightly longer than the visible spectrum, and the energy of these infrared wavelengths corresponds to the vibrational energy in molecular bonds. Every molecule has a unique absorbance depending on the structure of the molecule, just like differently shaped bells produce unique sounds. The absorbance spectrum for each molecule is so unique that it's often referred to as a molecular fingerprint. Beer's law takes the identification of the molecular fingerprint a step further, stating that while the shape of the absorbance spectrum is fixed, the intensity of the spectrum depends directly on the number of molecules present. Stated simply, the optical absorbance is proportional to the concentration of the glucose. Well, there we go. We can qualitatively identify the glucose molecule using its molecular fingerprint, and we can quantitatively identify the amount of glucose present using Beer's law. That should be everything we need to measure glucose using quantitative infrared spectroscopy. So what's the problem? Why hasn't this been solved years ago? In order to understand the problem, you should first understand the nuances of this measurement method. Quantitative spectroscopy is based on the Beer-Lambert law, commonly referred to as just Beer's law. Beer's law creates a relationship between the incoming intensity, I0, and the intensity of light exiting the sample, I. The log of this ratio is the absorbance of the sample. The absorbance is also equal to epsilon Cl, where epsilon is the molar absorptivity constant for the substance of interest, in our case glucose. C is the concentration of the substance, and L is the path length through the sample. Looking at this form of the equation, you can see that changes in concentration and changes in path length are indistinguishable in the overall absorbance of the sample. Increasing the concentration by x compared to increasing the path length by x results in the same increase in absorbance. In most applications, though, the path length is constant through the sample, and as long as that requirement of constant path length is satisfied, Beer's law is a powerful theory for determining concentration differences between samples. The difficulty with non-invasive glucose measurement is that the path length is not constant. Let's develop the concept of the path length histogram to really understand the problems of measuring glucose in tissue. Classic spectroscopy measurement applications use a light source and a detector positioned on opposite sides of a fluid sample with a defined path length designated as L. This type of sampling is known as transmission sampling. The photons from the infrared source go through the sample and are detected by the detector. The information collected by the detector is then processed to create a spectrum. If we examine the relationship between the length of the path traveled and the number of photons traveling that distance, we create a path length histogram. This histogram shows that all photons have traveled the same path length, defined by the optical cuvettes. In order to obtain an accurate calculation of the concentration of a sample, Beer's law assumes that all photons from the light source travel the same distance, taking the shortest path directly through the sample. In this example, Beer's law's assumptions are satisfied, since all photons travel the same path length. Now let's move to real measurements of glucose in biological fluids. Serum samples, which are blood with the red blood cells removed, represent a complex biological medium that can be measured using transmission sampling. Inlight Solutions conducted testing on serum samples obtained for intensive care patients and demonstrated excellent results. These data demonstrate that near-infrared spectroscopy has both the sensitivity and specificity to measure glucose accurately in complex biological media. A similarly accurate measurement can be obtained in blood samples with varying hematocrit levels. The data shown were generated by Luminous Medical Incorporated, a spin-off of Inlight Solutions Incorporated. Blood was withdrawn from a peripheral vein, then passed into a cuvette and measured with an NIR spectrometer. The left plot is a standard XY scatter plot, and the right is a bland Altman plot. The measurement results approach the error of the YSI instrument's reference. These data were part of a package submitted to the FDA. But there's a problem with this picture. Shouldn't the red blood cells scatter the light? And shouldn't the photons travel many different paths through the sample? Work conducted at Luminous Medical showed a surprising result. The vast majority of photons collected by the detector are photons traveling straight through the sample, having undergone just a few scattering events with only minor modifications in the path traveled. The photons that encounter many scattering events typically miss the detector and are minor contributors to the measured signal. Let's take a look at the different path lengths the photon could travel. A path length histogram is a graphical representation of the number of photons that travel a given distance through the sample. If we examine the path length histogram for the sampling of blood, we see that all photons have traveled at least L distance, while some have traveled a bit further due to scattering events. But the overall variance in our path length histogram is quite small, and this small variance adequately satisfies the requirement of constant path length for Beer's law. At this point in the video tutorial, we have discussed Beer's law and the assumptions associated with its application, discussed the path length histogram, and shown compelling glucose measurement results in human samples. The next tutorial will focus on spectroscopic measurements in tissue.